Yeah, let's consider other types of mass spectrometer. Uh, the three-dimensional quadrupole ion trap mass spectrometer. Yeah, it's use quadrupole. This electrode. Yeah? This is well suited as a chromatography detector. Yeah, like structure is given here. Here is a filament. Yeah, if in the filament, electrons are ejected. Okay, and here's the gate electrode. Yeah? Gate electrode admits electrons from this filament into the cavity. Here, this is cavity through the holes here, right? In the end cap, there are two end caps here, right? One and here, and at this side, the central ring electrodes are placed. Okay, and electrons are here, and then inside this cavity, molecules undergo ionization in the cavity. Okay, and here in the cavity, ionized and plus charged molecules are there, and apply the constant frequency and radio frequency voltage, yeah, these to uh, the electrode. Okay, yeah, central electrode, and then uh, these ions are what hmm, circulating um, in the three-dimensional orbit in the cavity. Okay, here ions are trapped, and its movement is circulation. This motion is a circulation motion. Okay, and there are all kinds of ions, and then the light ions. Yeah, ions with low mass charge, and it makes a large circle. Okay, and heavy ions makes the a small circle. Okay, and increase the radio frequency uh, between uh, these two electrodes, um, and the orbits get destabilized. Okay, and then some of them now fly away. Okay, out of uh, these end caps. Okay, in the end caps there are holes. Okay, yeah. So expelled ions now through they go through these holes and then enter this detector. Okay, yeah, that's the simple principle, and it has a high sensitivity, so you can mass down to 1 to 10 picogram can be detected, and scan from the mass to charge ratio 10 to 5 650 can be conducted 8 times per second. Okay? And resolving power is around between 1000 to 4000. Mass accuracy is 0.1, so this is not very accurate. The maximum detectable M to Z is to 20,000. Okay, this is called quadrupole ion masked ion trap. Ions are trapped here. Okay, ion trap mass spectrometer. Okay? Another type is linear quadrupole ion mass trap mass spectrometer. Okay, but here, trapped ions are making a circular motion. But here, linear quadrupole. This is quadrupole. Okay, 1, 2, 3, 4, and inside this quadrupole, ions are trapped, but in the linear fashion. Okay, has this one has higher trapping efficiency than this one, three-dimensional quadrupole ion trap. Okay, and higher storage capacity than 3D QIT. Ions are trapped inside in the central section or inside here, right? And by manipulating the voltages, okay, here apply the apply the voltages, ions of specific M to Z value can be expelled from here. Okay, they are commonly operated at unit resolution with scan rate on the order of this is scan rate 11,000 units per second, at the expense of slowing the scan rate to maybe 27 mass to charge units per second. A resolution of 0.05 m to z unit can be attained. Okay, and other type is called orbit trap. This orbit trap, the principle is not easy to understand, but okay, let me try. Orbit trap, I think this is the compound word for orbital and the trap. Okay, the orbit trap is a high resolution mass analyzer that does not require a magnetic field or radio frequency field. Okay, you don't need a magnetic field nor radio frequency field. Okay, the structure is like that. Okay, a very peculiar structure. Okay? Here, this is the picture. This is a resolving power. It has a very high resolving power of 150,000. Okay, so M2G accuracy of 2 to 5 ppm with external calibration. Oh, this is a very, the this is, I think, the kind of high resolution mass spectrometer. So upper limit of mass is 6,000 and dynamic range of several thousand. Here, trapped ions here inside that. You see, there are several electrodes. In the this one is central electrode. Yeah, the shape is curved like that. Yeah? Okay, and then there are two, electrodes, outer electrode. They are two. Yeah, the two electrodes are separated. Yeah, and so trapped ions, ions cannot penetrate this electrode. So ions are making this kind of peculiar circular motion around this central electrode, depending on the potential. Okay, ions are here, positive ions are here. So trapped ions circle back and forth around the central electrode as long as they do not strike another molecule. Okay, let's assume you have ions here inside this orbit trap, and ions are now making kind of circular motion around the central electrode, and they may collide. Okay, yeah. And then the collision makes the this one this orbit made different. Okay, look at that. Here is injected ions, and then ions inside the orbit trap makes this kind of motion. This is not a circular, maybe spiral motion. And then after the this motion is stabilized, it keep moving, it's having a motion like that. But collision, hmm, collision makes this orbit very unstable. So you have to maintain very ultra high vacuum inside here. Okay, ultra high vacuum is required. Ultra high vacuum is at least 10 to minus 8 Pascal, which is 10 to minus 10 torr. Yeah? In this high vacuum, is ultra high vacuum, mean free path is around 100 kilometers. Okay, the mean free path is the average path that the ions, okay, or species can travel before collision. All right, understand? Let's say in the when the pressure is high, there are a lot of species, okay, a lot of particles, and then one particle now move, and then immediately they hit another particles, right? So mean free path is quite small, but in this ultra high vacuum, mean free path is usually 100 kilometers. That means, let's see, there is one in a positive ion. Now it's moving, yeah, moving, and on average it moves 1 kilometers, and then it hit another ion, right? So there is a very small chance for this ion to strike, to hit other ions. Okay, well, this is schematics of orbit trap mass spectrometer. Here electrospray ion source, and then in this all these chambers are high vacuum are played, and here is this ion optics and the transport octapole. Anyway, this is linear ion trap with two electrodes. Okay, and then It's another. There is another transfer octapole, and this is C-trap. This, this shape is a C-type. Yeah? Arrangement of linear trap and C-trap for collecting ions, and comprising them into a small pocket and feeding the pocket into the orbit trap. Anyway, up to this point, this kind of preparation of ions, and then these ions are injected into this orbit trap through this hole in the end cap. Okay, and then this one, uh, these ions now have a trajectory. This kind of trajectory. Okay, a very stable trajectory, and here is the explanation. Ions from an electrospray source are accumulated in a linear ion trap and then transported in a one batch to a C trap, which electrodynamically squeezes them into a small pocket. Small pocket is ejected through an ion optics into the orbit trap. Right here is ion optics. During the 0.1 millisecond injection period, the electric field in the orbit trap, electric field is orbit trap is ramped up in such a manner that the ions begin to orbit the central electrode here, right? Not hitting the electrode there. After voltage on the central electrode reaches its constant level for stable orbits, detection begins. Okay, and then here, this is detecting a signal, right? And then by doing the Fourier transformation, and this pattern now is transformed into amplitude versus frequency. Okay, and this you know the different masses gives a different the frequency here. Okay, that's the principle of orbit trap mass spectrometer, and the resolving power is very high. Okay, let's stop here.